Now we turn our attention to how multiple threads can synchronize. There are three basic ways. The first is point-to-point synchronization. We've seen two realizations of point-to-point. First, we've seen post and wait synchronization starting in Lecture 5. Sometimes this is called signal and wait. Then we've seen send and receive when we first considered message passing back in Lecture 2. The second kind of synchronization is locking. A thread locks a variable before entering a region where only one thread can be allowed at a time. That kind of region is called a critical region. Then, after it's done modifying shared variables, the same thread executes an unlock operation which allows other threads to enter the region. This approach ensures mutual exclusion. If one thread is in, the other threads have to wait to enter. It is used, as we have seen, to serialize access to read-write concurrent variables. The third kind of synchronization is barrier synchronization. Barrier synchronization is used if all threads have to reach a certain point before any thread can get beyond that point. An example, as we shall soon see, is when a parallel program is checking whether a computation is converged. All threads must finish an iteration before it is known whether convergence has been reached, so a barrier is inserted before the test for convergence. Let's take a closer look at locking. Here we see a naive piece of code for summing an array in parallel. There is a for loop that is executed by all the processors. The code implements a free-for-all in adding to the sum. Any thread can add its contribution regardless of what the other threads are doing. What is the problem? The problem is that two threads may read sum and add their contribution before the other thread writes its updated value for sum. Then the second thread overwrites the value of sum, which causes a loss of the value added by the first thread. To prevent this, we can require each thread to lock a variable before it adds its value to sum. After it's done, it unlocks the same variable. This ensures that only one thread at a time is modifying sum. It prevents one thread from overwriting another thread's changes. However, if you look carefully at the code, you will realize that this isn't the only problem. Sum is now protected, but I is not. Two threads could try to increment I concurrently. If they did this, they'd end up with the same value for I and later add the same A sub I into the sum twice. So a complete solution would have to be more involved. When considering a lock implementation, we need to address two issues. Let's start with the second of them. Locking requires that all threads but one stop in their tracks. It tends to be very expensive, and that means that designers need to look at every opportunity to make it more efficient. How fast locking is affects the granularity at which we can afford to lock. We'd like to lock the smallest possible region because that allows the most concurrency. But that requires more frequent locking and unlocking, which has a high overhead. So there is a trade-off between the speed of locking and the amount of parallelism that is possible. Now let's look at barriers. A barrier affects all threads that are working on a single computation. Some threads may be faster than others, but all threads need to reach a certain point before any can proceed. Let's say before we can determine that the computation has converged. This means that faster threads need to wait for slower threads. Execution time depends on the slowest thread of all. So it's important to do load balancing, to try to structure the program so that all threads have a comparable amount of work to do. If one or more threads get suspended or swapped out, the whole computation is stopped. So rather than let the operating system scheduler decide which thread to run one by one, it's better to gang schedule the whole program so that all threads are loaded onto processors at the same time.